guys are doing well. Reminder to do your check-in and attendance before we get started in lecture today. And as always, I'm going to wait a few minutes and answer any questions. Good morning. I will remind those of you that are a little bit shy about asking questions on the live chat that I do have, or will in just a minute, have Teams open in the question and answer section, which I do need to shift over. Let's do channel. I think this is week 3, but I don't have my form on me, so okie dokie. So, good morning. So I've posted the start of the week questions, and I am going to that channel in Teams. So if you are shy and hesitant and you don't want to ask questions in the chat, in the live chat, you can also ask them in the Teams Q and answer channel so that you get your points. And I've got that up on my phone so that I may see it. I want to thank somebody stayed late. Sorry, my voice is a little high. I've got a little frog in it. Somebody stayed late on Wednesday night talking to me about the class and told me there was a way to get the YouTube live chat where I could see it more easily on my screen without having the streaming software loaded on the screen, which I find distracting because it has flickering lights and various other things that distract me when I'm trying to teach you guys, and it also distracts me from looking where the camera's at. And that was indeed correct. You could load the chat as a pop-out, but you have to do it from the actual YouTube live stream, not from the OBS software. But thank you for letting me know that you had done it before, so it was possible, because that got me looking for it. Because that will make this easier for everybody, and I wanted to put out a special thank you for that. So, the person who hadn't seen the whiteboard before, I'm being very careful to make sure I always save and name those whiteboards and share them. You do have to make sure that you log in using your login.cuny.edu app. It won't let you log in using your QMail app. You can download it as an app, so it may be like Teams. It may be just easier to download it as an app on your computer so that you can stay permanently logged in using the login.cuny.edu. For a while I didn't think you could download it as an app, but you can. So you can find that in your app store and download it as a separate app and then stay logged in using the same login. But that's available. Okay. So today we are going to finish our discussion, and somebody asked a question in Teams. I saw it while I was posting the announcement of when you're doing multi-step unit conversions, like going from pounds to grams to and quarts to milliliters in the same problem. Should we round after each step or wait until the very end? I'm not sure how it affects significant figures in the final answer. And that is an amazingly good question. And it all depends on, generally speaking, are you going to do that multi-step problem as truly as multiple steps, or are you going to do it in one line? So you're going to input it all into your calculator at once. So we're going to get to that today, but it's a very, very good question. And I will emphasize that question as we have lecture today, because it comes to the heart of the matter in terms of error and where it comes from. Now, part of what I will lecture on today is I will actually show you where the rules on doing calculations with significant figures, where they arise from. Now, generally speaking, I usually get asked, well, do we have to know this for an exam? And the answer is that depends on how you learn. I never like to learn rules without understanding where they came from. So for me, understanding where these, because you have two different rules, one for addition, subtraction, one for multiplication and division. And I never really liked memorizing those rules because I didn't understand where they came from. Once I learned where they came from, it made absolutely perfect sense why there are two rules. And the fact that those rules work most of the time, but not all of the time, which most books will tell you, but then you're like, well, then why are we memorizing them as if they're theorems in math that are, rigid? So I always go through and show students why there are two rules, and it does come back down to what we were already talking about, which is the nature of measurements and the units involved in measurements in comparison to numbers. So and we will end up, because of that, doing a little bit of statistics. For those of you that are going to medical school, you'll get to see a whole bunch more statistics, since you really actually have to take a course in that now for the MCAT. So those of you that are med school bound, when you're deciding on your calculus course, I would personally lean towards the calculus course for the social sciences, unless the other calculuses are required for your major. And that's because that calculus is going to be more of an applied calculus, and I think more relevant to pre-med. But certainly talk to advisors over that. Okay, so the first thing we need to do is talk about, in SI units, what do we measure? What are the standard measurements we make in the lab? Because those are going to be the standard SI units that we use a lot. And we've already mentioned mass. And mass is, technically the SI unit for mass is kilograms, which is abbreviated kg, which is 10 to the 3. That's what the K, or kilo, stands for, grams. So grams is the base unit that we build onto. And in the lab, in a chemistry lab, unless you're doing industrial chemistry or agricultural chemistry, you're going to be working in grams, not kilograms. Now, without a doubt, if you're doing agricultural chemistry or industrial chemistry, you will be working in the kilograms, not the gram scale. It's just a matter of scaling up, scaling down. Although, don't get me wrong, if you decide to major in chemistry, which we happily welcome you if you do, if you decide to major in chemistry and then decide you're going to get a job after you graduate with your chemistry degree, you could go into a lab as a person developing new drugs, or you could go into a lab as what's called a scale-up chemist. And generally speaking, the way drugs are made when they've gone all the way through a process and they're about to be marketed is completely different from how they were made initially by the first researcher to make them. And the scale-up chemist's job is specifically to scale it up so that you can make the maximum amount of that chemical in the shortest number of steps, wasting the smallest amount of chemicals. So it may be a completely different process. Scale-up chemists are very special. So going from grams to kilograms in a lab environment is actually not that easy most of the time. If you're going to do it in an efficient way and in an environmentally practical way. But that's mass. What other SI units do we use? Temperature, very common. And it's there are base SI units, and then I'm trying to remember the correct word for them if you're wondering. This base is not quite the right word. There are SI units that are fundamental, and then there are SI units that are derived. And the derived ones are basically built from the fundamental SI units. And we'll talk about those as well. Temperature, the SI unit for temperature is Kelvin. That's the unit that we use with the powers of 3 monikers that will also go for. So the prefixes like milli and mega. You would use that with Kelvin. It's abbreviated with a capital K. And more commonly in a lab, you're also probably going to use Celsius. And we use Celsius a lot in the lab. We tend to use Kelvin for negative temperatures because we don't like writing the minus sign. It looks like a dash. So we tend to use Celsius when we're talking about positive temperatures and Kelvin when we're talking about negative temperatures, because there is no negative temperature in Kelvin. So I'm going to give you the relationship between these two. What I'm not going to give you is Fahrenheit. And the reason why I'm not going to give you Fahrenheit is, while we do use Fahrenheit for temperature, weather in the United States, we don't use it in a laboratory situation. Occasionally, maybe a few industries may still use Fahrenheit, but it's very, very, very rare. Celsius tends to be the unit of choice in most industrial environments. So, there is an equation that converts Celsius to Fahrenheit. I'll talk about how you derive that equation. We give you that equation in your data book because it's just not worth memorizing anymore. What is important to know about Celsius is it's set by 2 points. Point number 1 is the freezing point of water. At 1 bar. The other 2 is 100. This is the boiling point of water at 1 bar. Some books will say 1 atmosphere, but technically by definition it's 1 bar. And those are the 2 defining temperatures for the Celsius scale. And then you just mark 100 lines. That's why it's also called centigrade for 100. you mark 100 evenly spaced marks between 0 and 100 to get you the rest of the temperature scale. Now, for Fahrenheit, the relationship is 32 degrees for the freezing point, and the boiling point is 212 degrees. And that's because Fahrenheit was originally defined by we'll do it that way. Fahrenheit was originally defined to try to make the average body temperature around 100. Now, usually if you see a capital T in an equation, that means temperature in Kelvin. And that is going to be the temperature, usually represented by a theta in an equation, and always when I'm doing it, in degrees C plus 273.15. And again, technically speaking, if I was going to write this equation absolutely correctly, that's how you would write it. Now, the way you get the relationship, these equations, is you plot T Kelvin versus theta degrees C. And so at 0 degrees C, I have 273.15 Kelvin. And at 100 degrees C, I have 373.15 Kelvin, and this line has a slope of 1 Kelvin degree per 1 degree centigrade. And literally, this is how you do that. So if I were going to do this for Fahrenheit, same type plot, and the slope because this is useful. You'd be surprised. Temperature in terms of scale, and like all measurements, we have to measure relative to something. So basically all scales are made up because you have to do your measurement relative to something else. Okay, so at 0 degrees C, I'm at minus 32 degrees Fahrenheit. And at 100 degrees C, 25, 50, 75, 100. 125. I'm going to run out of space. That's why I was making the face. Thank God for ropes. again. So 25, 50, 75, 100, 125, 150, 175, 200, 225, 212 will be right there. So roughly this is on my line. So this is 212. And this is my line. Okie dokie. So what's the slope? So this gives me theta in degrees Fahrenheit is equal to B times theta in degrees C plus A. Standard math. So slope, I need B, the slope is the difference of the y-axis divided by the x-axis. So this would be 212 degrees Fahrenheit minus a minus 32 degrees Fahrenheit divided by 100 degrees Fahrenheit minus 0 degrees C minus 0 degrees C. So this is 242 degrees Fahrenheit divided by 100 degrees C. Now, these are both even, so I can simplify them. So I get a 50 here. If I divide the top one by 2, I get 1, 2, 1. Just making sure. And then if I simplify some more, although that's 11 times 11. Oh, that's why I'm looking at this. Why did that not? 212. It's 32, not minus 32. You guys didn't catch me on that. It's like that did not give me the right math. It's 32 degrees C, not minus 32. So this should be minus plus 32. It's early and I am not awake. And this should be 212, so 0. 11 minus 3 is 8. Carrier 1, 180. Yes, okay. So now I get 18 degrees Fahrenheit over 10 degrees C. Because I can cancel that first 0. And then if I divide by 2, I get 9 degrees Fahrenheit over 5 degrees C. So that's the first step. That gives me the slope. And then I have to know one additional temperature to get the intercept. So at 0 degrees C, so now I have degrees Fahrenheit is equal to 9 degrees Fahrenheit over 5 degrees C times theta in degrees C plus A. In order to get A, I just need to pick, and it doesn't matter which one you pick. I can pick 212 and 100, or I can pick 32 and 0. 32 and 0 will be the easier point to pick. So at 32 degrees Fahrenheit, I'm at 0 degrees C plus A. So that means A equals 32 degrees Fahrenheit. And that means my final equation for the relationship between the two is degrees in Fahrenheit is equal to 9 degrees Fahrenheit over 5 degrees centigrade. Theta in degrees centigrade plus 32 degrees Fahrenheit. And then, always, when you're working out equations with units, check your units. Degrees centigrade cancels degrees centigrade, leaves me degrees Fahrenheit, which I'm then going to add degrees Fahrenheit to get a final answer in degrees Fahrenheit. This works. That also means when I'm solving it the opposite direction, I also have to check for units. And I have to be very aware of units. So to solve this to get for degree C, first thing I have to do is, and I do recommend you guys practice doing math in your head without drawing all of the steps you used to draw in algebra. So to solve this for degree C, I need to move this 32 over to the right-hand side, and then I need to move this over to the, left-hand side. So that means I would need to take theta in degrees F and subtract 32 degrees F from it, which is something I can do. They both match in terms of units. And then I need to multiply to get to degree C. So that's the other version of that equation. So that's how you relate temperature units. And that means you can use anything as a temperature unit. You just have to have 2 points and tie it back to something you already know. And this is how we calibrate thermometers. And that's why I went through this. When you purchase a thermometer, because a lot of times the thermometers that we purchase, like the thermometer you purchase to measure body temperature to tell if you have a fever, that thermometer is a digital thermometer. The way that thermometer works is it has inside the tip, there's 2 ways it works, and you can tell which one you have. If your thermometer has a little bit of metal, it's covered by plastic, but you see a little bit of shiny bit at the bottom, and then you see like 2 wires that kind of twist up through the plastic up to the top where it displays the temperature. That particular thermometer works is what's called a thermocouple. And we're going to discover and discuss and describe how that works. But in essence, it is 2 wires of different metals twisted together. And because the metals are disparate, they're different, those 2 wires chemically react with each other, and in something called an oxidation reduction reaction, and all chemical reactions are temperature sensitive. So you get a current due to that oxidation reduction reaction that is going on between those 2 wires, and the amount of current you get increases as a function of temperature. Not linearly, by the way. So what you do is you take that junction of those 2 wires and you put it in different temperature baths. You put it in a water bath, freezing water bath. You put it in a boiling water bath. You put it in freezing acetone. You put it in boiling acetone. You put it in freezing ethanol. You put it in boiling ethanol. And that gives you a whole bunch of points on a temperature scale. And then you plot those points and you get an equation. It doesn't happen to be a linear equation, but you get an equation that relates current output to known temperatures. And that gives you a way of converting current to temperature. And that's called a calibration curve. And that's how all of the digital thermometers work. Is you're either measuring a voltage or you're measuring a current, and from that, because of calibration and equations, you can induce a temperature. In other words, you can calculate a temperature. But that's not what the actual digital thermometer's measuring. Um, what the thermometers you use in the lab are measuring is a change in density. And since the volume is confined, the when the density changes, the volume goes up and down because the amount of material is confined. And that's why you get the level going up and down. So that's temperature. And that's a standard one. Another standard one is length. The unit of measure for length is meter, and it is a lowercase m. Now, I'm so sorry to tell you, we use that lowercase m for everything. In equations, if it's in an equation, we use it for mass. So if you see a lowercase m in an actual equation, it's mass. If you see it at the end of a number, it's meters. It's a unit. So you have to know in context, and if you see it before a unit, it's milli. So you have to know in context what that lowercase m means. So for those of you that struggle a little bit with this, practice with the lowercase m because we use it for a ton of different things. Time. Our base unit for time and also the SI unit is seconds. And what this means is you're generally not going to see a plot in minutes or hours unless it's really, really something that's slow. And then it will be in minutes, but you're going to convert the minutes to fractional minutes. So you're not going to write like 49 minutes, 30 seconds. You're going to write 49.5 minutes. So time, generally speaking, is in seconds. And then for chemistry, quantity of substance. So mass is one way of telling how much of something you have. Another way of telling is how many particles are making up that mass. And that's quantity of substance. That's a mole, and we normally abbreviate it MOL. Now, I've never quite figured out why we abbreviate mole MOL, since really is it that much shorter writing MOL versus MOLE? I don't know, but that's the abbreviation for mole. We couldn't use M because it's meters. Now, there's two other quantities that we will get to, but we won't use it in 113. We will use it in 114. That's electric current. This is kind of a base unit. It's an amp. Abbreviated amp. And another one is luminosity. That's how bright a light source is. And its unit is a candle mark. I don't tell you, we almost never use this unit. I've in fact never seen this unit used. Think it's a candle mark, but I don't want to tell you wrong and then have you guys go look it up on me. So give me new window. A candela. Or CD. And this is luminosity intensity. And I suspect, based on what popped up when I Googled that real quick, is that's predominantly used in astronomy for stars, which would make some sense. Generally speaking, on Earth, we use watts, so that's definitely not. We talk about power, the power of a light source, not necessarily the luminosity of it. Okay, so that's it. That's the base units. Now, when you're writing, it's one thing. So if I am writing in my research notebook something like the length, well, if it were a research notebook entry, and I'm measuring something, I might write diameter, length. And then I'm just going to write whatever I measure. So like 9.56 centimeters and say 257 centimeters. And there was a chat. Give me just a minute. I'll get to that at break, Nicholas. Okay. Now, if we were to write this, notice I have it in centimeters. If we were to write this in meters, this would be 0.00 0.956 meters. And this one would be 2.57 meters. Yep, okay. And that's fine, but when you get to really, really small objects like 0.000000856 meters, do you really want to have to write all those zeros all of the time? No. Or 1.2 comma 2 Neither one of those are going to be uber convenient to write down as units, as measurements. That's a pain. That's a lot of zeros to write. And in both of these cases, these zeros are insignificant. That's correct. We would use scientific notation to condense it. So I would write this as 8.56 times 10 to the 2, 3, 4, 5, 6 minus 6 meters. This one I would write as 1.2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bytes. Now, that's perfectly fine when you're writing, handwriting, with a pencil or a pen. That's a pain in the rear end to typeset. It's a pain to typeset even on a modern computer. Think about if you guys were typing a report, what you'd have to do to get that number in. You could type the 8.56, space, Then you'd have to go to symbols, insert, find the little time symbol, insert the time symbol, space, type the 10, go to the symbols, insert the correct mathematical symbol for the minus sign, and then the 6, and then probably you would hit space and meter, and then you'd have to go back and you'd have to highlight the minus 6, and you'd have to superscript it. That's a lot of steps to write that number. And by the way, modern computers, that's a lot easier than it was if you were using a typewriter. With a typewriter, you would have a set of special keys that you would keep at your desk, so that when you needed when we finally got to electric typewriters, you had a special scientific ball that you actually snapped into your typewriter when you needed to write in science. But yeah, you would have to 8.56 change balls, do the times, change balls, 10, roll the paper down, minus 6, roll the paper up, meters. Still a pain to typeset. Because of that, in SI units, we developed a way of denoting this 10 to the minus 6. That we denote with the Greek letter mu, and it means micro. We developed a way of devoting 10 to the 12. That we denote with a capital T, and it means tera. So now I can just write this 8.56 micrometers. This one I can write 1.2 terabytes, or TB. That's why I picked that one. That's a standard hard drive size, 1 terabyte. So, the development of prefixes on SI units was to basically reduce the load when typing and typesetting load when writing research papers. That's why it was developed, was to make the transmission of scientific data easier in written form. Now, your book probably has a really big table of all sorts of different SI units. There's really only a handful of SI units we use in SI prefixes that are commonly used in the lab. So, and they're used in really specific locations. So, exa, E. This, the only reason why I'm introducing it is we now have a computer that can calculate exaflops. A flop is a calculation per second. So you're only going to see this in computers. Peta. We've had petaflop computers for a while, but they're rare. So the U.S.'s petaflop computer was at Oak Ridge National Labs, and we compete with China, who also has a petaflop computer. We recently upgraded that petaflop computer. That's now why we have an exaflop computer. I'm sure China's in the process of upgrading their petaflop computer so that it'll be exaflop. We're also in the process of building a second exaflop computer in California. These high-speed computers, their dominant time is used calculating the weather, but then you can also, as scientists, get time on them to run your own calculations if those calculations are deemed scientifically good, if they're important enough to take time on a computer like this. So you have to submit a research grant, and your grant is judged, and based on that grant you're given a certain amount of time on the computer to use. Tera, is it 2 R's? No, it's 1 R. I did 2 there because I'm used to Earth. Capital T, 10 to the 12. And notice how these are 3 decimal places apart, basically. They're 3 orders of magnitude apart. They're 1,000 apart. So that means when you get to 0.856, you're now at 856 of the next lowest one. So that's kind of how they're designed to be. Giga. I'm going to move these down just a little bit. Tera. Giga. Mega. So these 2 are kind of exclusive to computers right now. These 3 you will see in comp sci, although we've kind of expanded past those. But you'll also see these in spectroscopy, which is something we will get to, especially in terms of measurements of frequencies. And that's also true for kilo, which is the next step. Now, these, I actually do not expect you to know. I will remind you of those 5 if we use them. I will remind you of them. I'm showing them to you because depending upon what your major is, you may end up using these a lot more than we use them in chemistry. So the next one is kilo. Okay. 10 to the 3. You will see this in frequencies in spectroscopy, but you'll also begin to see this in masses, in distances. So this is not uncommon for mass, for distance, i.e. lengths, as well as frequencies. So that's kind of the dividing. Now the hecta and deca, we don't use them. We tend to stick to powers of 3. So those, just mark them out of your table. You're not ever going to see them. Now, when we move down the other direction, I'm going to put these in. I'm actually going to also put this one. I'm going to put kilo in red because you are expected to know that one. The next one I expect you to know is centi. And that's 10 to the minus 2. And then milli, which is a lowercase m, that's 10 to the minus 3. These are very common measurements in the lab. These are, this one is mostly distance, so lengths, and it is really important in volume. We'll talk about that in a minute. Milli is distance, volume, concentration. So that one, mass. So that milli, really an important one. Now, when you move down, and again, I am going to expect you to know this one, micro, submu, 10 to the minus 6. This tends to be volume, at least when you're used in lab, and length, for those of you in microbiology. Cells tend to be on the order of 10 to the minus 6 in size. So that's why micro is used. Now, I'm going to swap back to black because, again, these, I do expect you to be able to convert between them, but I don't expect you to actually memorize the size. I will give it to you. If we're going to use it, I will remind you of it. But nano, N, 10 to the minus 9. Pico, lowercase p, 10 to the minus 12. Femto, lowercase f, 10 to the minus 15. And atta, lowercase a, 10 to the minus 18. Nano, micro you'll also see in concentration. Nano you'll see predominantly in concentration and size, so length, and time. And this one you'll also see in time. Pico, femto, and atto are all tend to be units of time. You can measure, it's hard, but you can measure something to an attosecond. So 10 to the minus 18 seconds. So those tend to be on the order for time. Now, other places where you'll see nano is in spectroscopy. I'm going to slide this over like this. Because the wavelength of light for visible light, the distance between peaks in the electromagnetic field that forms visible light, is in the nanometers. And in fact, in spectroscopy, we have another and also in chemical measurement. This is one of those that I want you to begin to get used to seeing. So I'm going to put it in blue. And that is angstroms. It has a very special unit. It's a capital A with a little dot on top of it. It is specifically used for wavelength, for size, in other words. So it is specifically 10 to the minus 10 meters. You're it's not going to be associated with any other SI unit. It is specifically associated with length only. But it is used in spectroscopy, in light, the measurement of light. And it's also used in biology in the measurement of cell sizes, because it's kind of right at that perfect size. That's why they made a special unit for it, because they were writing like 50 nanometers all of the time, or 55 nanometers, and they just finally just said we're going to write it as 5.5 angstroms. So that's why angstrom was invented, but it is a specific relationship. It's only for meters as a unit. So when you see A with a thing, it's going to be all by itself as a unit. It's not going to be attached to anything else, and it means 10 to the minus 10 meters. Okay? So the units in red I expect you to have memorized. The units in black I expect you to be familiar with, and we might use, but I will remind you of what they are. And what you really need to be able to do, and this is something you should practice doing in your head, is you really should practice being able to quickly move. Like if you see 353 millimeters, you should also pretty much instantly go, oh, that's 0. Micrometers. Oh, that's 0.353 millimeters. Or if you see 0.353 milliliters, oh, that's 353 microliters. And the reason why you really need, especially this last one, to be able to do that in your head, for all of you that are going to be biologists or chemists, we use microliter pipetters, and you dial the volume in microliters. But you tend to be adding this to milliliter additional volumes. So it might be you're diluting micro broth down. So you're going to take 10 microliters and add it to 100 milliliters. So you need to be used to interconverting between micro and milli. That is the dominant one. So you tend to need to be really paying attention to those powers of 3, because those tend to be where we just instantly start moving decimals around. And why? The truth is we're lazy. It reduces the number of things we have to write down. If I want to write 0 for milliliters, I have to put a 0.353 for milliliters. And I can write 353 microliters. It saves me from writing 2 things down on a label. And if you got a really small vial that you're putting this in, having smaller amount of stuff on the label makes it easier. So it really is about convenience. But all of these prefixes on units are about convenience. So now that we've got some units, now we can do conversions between units, which we will do after the break. So we are about to go on to our 10-minute break where I will answer questions. I know the break says 5-minute countdown. I'm sorry, I got to fix that. But it's technically a 10-minute break because we didn't take the first of the breaks. Okay, Nicholas. Going through this again, homework is always going to be done in class. We meet again on Wednesday. That's when you will do your homework. When we are meeting when we're meeting both classes online, like we will do next week, Wednesday would normally be our in-person class. I will set aside the last hour of Wednesday for you to do your homework. Homework will still be due electronically on Wednesday. If you do not finish it during that 1 hour class time because you didn't work it until I gave it to you on Wednesday, the homework requirements, then you will have until Friday to submit it electronically, but you will lose 2 points. I did relax the requirement that it be dropped off in person. In other words, a lot of students were like, if we are meeting solely online, why do I have to come into Queens College to drop the homework off? I was like, well, okay. So I have relaxed the requirements of dropping the homework off in person. I am going to set it up where you can submit it electronically and you can work it electronically. I handed the homework out as a hard copy last class period. But the requirement is it still must be handwritten. If you type it, I won't grade it. You can either handwrite it in OneNote, or you can, because I'll provide it both in OneNote and as a PDF file. You can either handwrite it in OneNote, or you can print the PDF file, write it on the PDF file, then take a picture of it and reconvert it to a PDF file, because I am not grading 20 pictures either. So it's your responsibility to either know how to use your all-in-one printer or know how to use a picture app on your phone to convert it back to a PDF and submit a single PDF of your homework. And it's your responsibility to make sure I can read it if you're going to submit it electronically. Now, if you want to submit on Friday and you do want to come into Queens College and drop it off, you can drop it in the mailbox by my office door. What you cannot do, as somebody found out on Friday, is you cannot interrupt me and ask me where to drop it off. And don't go into the department office and say, I need to drop this in Dr. Evans's mailbox. They're going to put it in my mailbox in the office and it won't be graded. I have a mailbox by my door at Remsen 211. It's a black box. I will put a sign above it that says Dr. Evans mailbox. Students who choose to drop it off in paper, I'm going to have a research student when I'm not there check that mailbox on Friday. He's going to take those. He's going to make sure there are no staples. He's going to scan them as a single PDF file, and he's going to send them to me in Teams so that I can grade them. So if they're not in that mailbox, he's not going to get them. They're not going to be graded. You'll earn a 0 on that homework, and you'll remember to drop it off in the correct spot. So, where does it go, guys? Make sure that I didn't just become Charlie Brown's teacher. When is the homework due? Somebody post it in the live chat, please. Either chat. You can post it in the Teams chat if you don't want to post it in the YouTube chat. But when is the homework due? With no bonus. That'll work. But you can also just turn it in class. When is the homework due if you are late? When is late submission due? Come on, Zachary. You had the right answer on the first one, so you can have the right answer on the second one. Yep, that's it. Thank you, Andrew. Now, the other thing I will remind you of is starting in Chapter 2, which we will be on Wednesday. Some of the suggested homework will come from the guided inquiry, chemistry guided inquiry, the required book for the course. I will not be providing the worksheets for that book. If you haven't gotten your book yet, you may chat me privately in Teams chat with a picture of your receipt showing you purchased the book and its date when it will arrive, at which point I will send you personally in Teams chat the particular suggested worksheets. But I will only do that until the time that your book arrives. And that's because I am not going to violate book copyright policies. But that will start probably suggested homework starting using the guided inquiry book will go up today, tomorrow, because it'll start for Chapter 2. And the book just doesn't have anything in Chapter 1. And the same for the bonuses. Out of the CHEM Connections, which is optional. Now, Darn it, darn it, darn it. Speaking of which, okay, there is a seminar today that you can do for bonus. Give me just a minute. I should have the Zoom link. In my there it is. So I'm going to add that to the team's classwork. And so this is Zoom talk by okay, and then the final thing I need to add is so, as I told you guys, I would try to make sure that if you did want to buy that other book, that you'd have the option of doing other possible bonuses that would get you the same that would eventually add up to that would eventually add up into the same 100 points. This is such an example of that. Schedule date, it's fine. Due date should be 10/11/59. Close date Friday 11/59. Done. Publish. Okay, so there's your first bonus assignment for attending that seminar. It's uploaded for you guys. And at the next break, I'll do the same thing for the 114 students. Okay, so let me flip us back to the whiteboard, and we can go back to this. So again, the ones in red must memorize. I will expect you guys to know those. The black ones I will remind you of. The blue one is a special unit that we will use, so you should become familiar with it. Now, these units up here, length, time, quantity of substance, temperature, Celsius and Kelvin, and mass, are again the units that we are going to be most commonly using from the derived units. I mean, from the standard SI units. But the truth is in chemistry, the dominant SI units that we use are mass, moles, so quantity of substance, and temperature. Which most chemists, by the way, quantity of substance, most chemists just call that moles and go about their business. Mass, quantity of substance, and temperature. Now that doesn't mean that's all the units we use. That's all of the base SI units that we use. Now, there are derived units that we use all of the time. Derived units are the units you get when you take those base units and you add them, you multiply them together with other base units. A good example of this is area. Area of there's several areas, there's several volumes that we use. Although area again is more of a physics than a volume, physics unit, but so area is not something we use as much as volume. So area, if it's a square, is length times width. If it's a circle, it's pi r squared. So this is for a rectangle. This is for a circle. Same thing gives you area for both of them. R here is radius. And I will remind you in a little aside that if you have a circle, which I suck at drawing, so please don't laugh, the radius is half the size of the circle. So that's the radius. This is the diameter. So the radius is the diameter divided by 2. And I'm saying that specifically because a common mistake that's made when doing homework problems or problems on an exam is you're asked what the volume of a bar is, and you're told the bar has a diameter of 0.25 inches, for an example. And that's because if you are measuring in class the size of a bar that's round, you're not going to measure its radius. That's too hard. You're just going to measure its width. And that means you're going to have to take that width and divide it by 2. And it's exactly 2. So when talking about significant figures in measurement, precision of measurement, an exact number has infinite precision. And what that means is it doesn't impact the significant figures of what you write down. You don't have to worry about it. And that's exactly 2. Now, pi is not an exact number. So if you say pi is 3.14, you have limited your measurement to 3 significant figures when you do this multiplication. And if you know your radius to more than 3 significant figures, you have to look up pi to more than 3 significant figures. So when you are using fundamental constants, such as pi, such as a huge number of fundamental constants that we will use in this class, you have to make sure that you are using fundamental constants at the same precision or higher than what you need them to be in terms of what you're calculating, so that it is not your fundamental constant that impacts the precision of what you write down. You should not be rounding to the significant figures of a fundamental constant. We know those things out to like 13 decimal places. So your fundamental constant should not be what's dominating the precision of a calculation. Just go look up, use them to a higher precision than what you've got memorized. And that means you'll have to look them up. That's in your data book. Anyway, in either case, the unit of length and width, and that's a distance, and the unit of radius is also a distance. So those all have fundamental units of distance. So that means that their unit is, so the unit of area, we usually write area as a capital A. So area is equal to length times width, and that means meters times meters, or meters squared is its fundamental unit. But it's a derived unit because square meters, or meters squared, is not one of the base units. Distance is a base unit. Meters is a base unit. Meters squared is a derived unit. It consists of 2 base units that are multiplied together. One much more commonly used in chemistry is volume. Now, volume, symbolized by a capital V, would be, if you're looking at a box, length times width times height. This is for a box. Pi r squared h. This is a cylinder. And pi r 4/3 pi r cubed. This is a sphere. So those are the 3 volume equations. In all instances, they involve 3 different distances, either length, width, height, or 2 radiuses in height, or 3 radiuses. But in all instances, they involve 3 distances, so distance cubed. And that means the fundamental unit for this is meters times meters times meters, or meters cubed. And the problem with that is a cubic meter is huge. That is a big volume. So that base unit's not the most convenient unit. Technically, in chemistry, and science in general. Our unit for volume, in other words, the SI unit for volume is a liter, not a gallon. That's the US units. You are not going to talk about milligallons. You're going to talk about milliliters. Now, a liter is by definition 1 decimeter cubed. So that is 10 to the minus 3 meters cubed. Like I said, cubic meters huge. That's more swimming pool size than lab size. So we use liter. In a laboratory, small scale laboratory, like what you guys will be using, you're not generally even going to use liters, you're going to use milliliters. The stock room's going to make liters, you're going to be using milliliters. So 1 milliliter, lowercase m here is milli, and that means 10 to the minus 3. So that means this is equal to 1 times 10 to the minus 3 liters. Now, this would be 10 to the minus 1 decimeter times 10 to the minus 1 decimeter times 10 to the minus 1 decimeter, which is 10 to the minus 2 meters times 10 to the minus 2 meters times 10 to the minus 2 meters, which is centimeters cubed. Let me write this, which is centimeter times centimeter times centimeter, or centimeters cubed. So 1 milliliter, 10 to the minus 3 liters equals 1 cubic centimeter, or 10 to the minus 6 cubic meters. See, we're stepping it down even more. This is a set of units you really need to know and be comfortable moving between. And I don't just mean that for this class, because if you work in pharmacy or as a nurse or as a doctor, 1 cc, standard dosage auto syringe, cc stands for cubic centimeter. So 1 cc is 1 milliliter. So that's one of those units you just got to be able to convert between and be comfortable with. But again, it's a derived unit. Base unit is a distance, meter. Volume is basically cubic meters would be the base SI unit for volume. It's just, that's way too big a volume to be practical for most applications. So we create a different unit that is more practical for everyday use. Now, something to keep in mind, this is in your data book, so it's not something you need to memorize, but 1 centimeter is 2.5, sorry, God. Brain's not working still. 1 inch, US measurements, is 2.54 centimeters. And that's an exact value. An inch, if you're curious, and I need to be able to see my camera so that I can make sure you can see my finger. An inch is the average length between this knuckle and this knuckle on your right hand. I think it's technically, yeah, your middle finger. That's an inch. And a lot of our measurements in what are called British standard units or British units or American units at this point are basically measures from the body. So a foot is basically that length. And you can think about that if you're like winding a rope around your from elbow to hand. Each wind is 2 feet. So 2, 4, 6. So it's a very convenient unit of measure. So that's roughly a foot. A yard is roughly from fingertip to collarbone. And the same thing, if you were measuring like fabric and somebody wanted a yard, you would just measure to there and you would cut. So, and at the time when this was happening in medieval Europe, that's actually how they would measure stuff. And then, of course, you would get slightly different lengths based on the average length of a human forearm. So if you had a really long-armed person, you might want them to do your measuring of length because you'd get more for your money, versus if you had a shorter-armed person. And so eventually that got standardized into a fixed standard, and those standards were supplied by, at least for lengths, by ropes with knots in them. Because that way you had a fixed size, or by sticks with a fixed size. And those standards were provided by the government. And it was because, well, they got tired of mediating arguments over getting shortchanged because one person measured the 2 feet versus another person that had longer or shorter arms. So volume is one of those units you're flat out going to use. The other unit in chemistry that we are going to use a lot is pressure. Now the problem with pressure as a unit is there are a ton of units for pressure because it is a very derived unit. So there's so many different ways you could go about doing this. So pressure is by definition, some people use a capital P, other people use a lowercase p. I tend to use a capital P because in physics lowercase p is momentum. So pressure is by definition force per unit area. Now, this is how you go about doing derived units. Does anybody happen to remember the absolutely famous equation for force? Newton's equation. Well, can anybody pop that into chat? Yep. So force, it's not distance times time. The one I was looking for is mass times acceleration. There you go. Force is equal to ma. So mass, distance times time is work. You were close. We'll get to that one. So mass times acceleration. Now, force, F equals ma, is a famous equation for Newton. So force has units of newtons. That's his equation. We give him the name for the units. Now, newtons is a derived unit, and you can use Newton's equation to give you the unit. So the unit for mass is kilogram. Acceleration is distance per time squared. So kilogram meter per second squared. So that's what a Newton is. So 1 kilogram meter per second squared is 1 Newton. If I plug that into the pressure equation, so pressure has units of force, so Newton per area meter squared. A Newton is a kilogram meter per second squared times 1 over meter squared. That meter cancels that. So now I get kilogram per meter second squared. That's the pressure unit. And this we call a Pascal. Or P, capital P, lowercase a. So a Pascal is a Newton per meter squared. And much like the unit of volume being meters cubed, Pascal sucks as a unit. It's just not the right scale. It's the right units in terms of SI. It's just not the right scale. So what we do is we define a bar relative to a Pascal. So So 1 bar, which is the SI unit for pressure, is 10 to the 5 pascals, or more frequently 100 kilopascals is how you'll see it defined. But 10 to the 5 pascals is the correct unit for that. Now, you guys are more used to talking about from high school pressure in atmospheres. Again, the change from the SI committee from atmospheres to bar happened in the 80s. So it happened before even I went to college. And the books were like, oh, well, we'll change it eventually, but it's the US and, you know. And they've just not ever changed it. And what's even worse is a lot of textbooks will specifically still define standard temperature and pressure in atmospheres, not bar, when that standard was changed in 88, I do believe. So that is a real issue. Now, it doesn't cause a real issue because a bar and an atmosphere are really, really, really closely related to each other. So 1 atmosphere is 1.013 bar. So it's really, really close, but they are slightly different. And because they are slightly different, and because certain things depend upon pressure, like the temperature at which things boil, thermodynamics values like enthalpy and Gibbs energy and a whole bunch of stuff in chemistry related to energy depend upon pressure, that slight difference between atmosphere and bar shifts the values in the measurements in that second decimal place, because that's where the difference arises. So you have to be really careful when looking online at thermodynamic tables that you're going to use if you're using an online homework system. Because if you're using an online homework system, the online homework system is going to presume you're using whatever thermodynamic data they're providing. And a lot of times that data is in atmosphere, but then if you go look it up online, those data are going to be in bar. And it's going to be off in that decimal place. And if you're adding a whole bunch of numbers together, that 0.01 eventually adds up and affects the first decimal place. And that's going to get you marked wrong in online homework. This is not going to impact the homework I do, because I build in that error between if you look up your data, and I will be pulling the numbers out of your data book for things like quizzes and stuff. So if you use your data book, you'll have the correct answer. Now, there are a couple other units that we use pressure for that you have to be familiar with. This you need to know. This you don't really need to know, because we really do not use Pascal in pressure units at all. Never seen anything in pressure quoted in Pascal in chemistry. I've seen it occasionally in physics. What we do use is millimeters of mercury, which is also called a torr. And this thing is defined relative to atmosphere. So 1 atmosphere is 760 torr. And that's because I don't know where the 760 came from. I really don't. I'd have to look up historically why we marked 1 atmosphere at 760. The reason why it's millimeters of mercury is because originally our pressure gauges were made of liquid mercury. And at 1 atmosphere, you would mark a line, and that was 760 torr. So I just don't know why we divided it by 760. That I'd have to look up. It seems an odd thing. Why not divide it by 100 type deal? But I'm sure there's a historical reason for that. I've just never bothered to look it up. You are predominantly going to see torr in what's called vacuum conditions. So this is again one of those things where the units you pick are based on just historical usages. So at 1 atmosphere or bar, you're just going to stay at bar. And then if you begin to pump air out of something, you're going to pull a vacuum on it, and eventually you're going to get to 1 millibar. So this is 10 to the minus 3 bar. So I'm pulling a vacuum. And if I continue to pull a vacuum, I'll get to 10 to the minus 5 to 10 to the minus 6 torr. And this is what's called high vacuum. Now, let's see what that is in bar. So 10 to the minus 5 torr. There's 760 torr. in 1 atmosphere, and there is 1.013 bar in 1 atmosphere. So that is, oh, it would figure I don't have a calculator on me. Gotta remember to grab one and put it here. 10 e to the minus 5 times 60. So that is 1.3 times 10 to the minus 7 bar, or 13 microbar. No, 0.13 microbar. Move the decimal to the correct place. Now, you saw me pause and think about that before I did it. Always, always, when you're moving the decimal place to get to an appropriate unit, stop and ask yourself, is that reasonable? Did I move the decimal to the correct direction? Because it's easy to make that mistake. So this is, we're pretty low. But from a physics community perspective, from like my research perspective, this is not uber low. You would not do, there's a significant number of physics experiments you wouldn't do in this type of vacuum because it's still got too much air. So a lot of physics experiments happen in what's called ultra high vacuum. Ultra high vacuum is kind of defined as 10 to the minus 8. That's on the poor end, to 10 to the minus 11. That's kind of almost impossible to do in the do on Earth atmosphere. Torr. So the 10 to the minus 11, you're going to be barely there. And most vacuum gauges won't measure it. They'll measure 10 to the minus 10. But so 10 to the minus 11, that's pushing as good as you can do on Earth's atmosphere. Because you're kind of almost at the stage where stainless steel starts evaporating slightly when you're at that level. That's still not the vacuum of space. Space is even lower than that in terms of pressure. And then if you go past the heliopause, where the particles that the sun's spilling out are no longer have the energy to keep going, the vacuum's even lower than that. So, but on Earth, if you hear somebody talk about ultra high vacuum or UHV, this is called abbreviated UHV. This is the pressure that they tend to be in. And like I said, I have no idea why we still use torr for that, but it's historical. And when you work in this region, you're not going to call it bar or atmospheres. You're going to call it torr. And all of your pressure gauges are going to be in torr. So pressure tends to be one of those units. We use it a lot. We have a ton of different units we use, and that is really rare. Because usually in the sciences you have a set of units, and those are the units you use all of the time. So for chemistry, mass, grams, maybe milligrams. For concentration, moles, millimoles. For temperature, Celsius, maybe Kelvin if you're working a lot at negative Celsius degrees. But for pressure, atmosphere, bar, torr, all of them are commonly used in a lab. So that's the place where you really have multiple units with multiple meanings, multiple scales. So I apologize for that. Okay, so to answer, because I did say that I would answer this, and we will finish chapter 1 in terms of calculation, and we're going to work problems. So on Wednesday in class, the first hour I'm going to work problems from chapter 1. And then the second hour you will do your homeworks and then submit your homework. But to answer the question of what do you do when rounding significant figures when you're doing a calculation, you usually, to prevent, if you're doing these calculations in multiple steps instead of a single step, you don't round to significant figures for each step, because you will induce a round off error. You were right to ask that. But you also don't keep everything your calculator gives you. So say I'm doing a problem where I have a cube that is 3.56 centimeters times 3.2 centimeters times 2.567 centimeters. Why I would be measuring the different lengths like that, I don't know. Maybe different people measure the height, length, and width. And it has a mass of 35.368 grams. And I want to know what the density is. Well, I know density, mass density, is mass per volume. And since it's a cube, I know the volume is the length times the width times the height. So I've already got that written out. So if I do that, I get 3.56 times 3.2 times 2.567, or 29. Now, the rules for a significant figure when multiplying and dividing is you keep the least number of significant figures. So this has 2 significant figures, this has 3 significant figures, this has 4 significant figures, so I should keep 2. But because I'm going to use it in a future calculation, I'm going to keep 1 additional significant figure, and I'm going to put a bar over it to indicate in my calculations that that's insignificant. That's a really good way of maintaining and keeping track of how many figures are significant, so that if you're doing a really long, complicated calculation, you don't have to go all the way back to the top and follow your significant figures through. So by putting a bar over the insignificant figure, I'm saying, okay, when I get to the end of this problem and I get my final answer, depending upon the rules, that number that I'm keeping right there is insignificant. So then density is 35.368 grams divided by 29.2 with that bar milliliters. And that is 35.368 is 29.2. 1.2, and again, for division, it's determined by significant figures. I have 5 significant figures here. I have 2 here. So 1.21, put a bar over that, grams per milliliter. And if that's all the question's asking, I'm not going to use the density for something else, then I would just write this as 1.2 grams per milliliter. Because now I've kept track of the precision. Notice I did not write that as an approximate. It's not an approximate. That is the answer. That is all of the value I can give based on the precision of my measurements. So I am not approximating. I am reflecting the precision of the measurements that I have. So when we work problems on Wednesday, I will explain why these rules about addition and subtraction, multiplication and division in terms of significant figures as part of that lecture. And we will practice, and we will practice a lot. And the reason for that is this is General Chemistry 1. And because this is General Chemistry 1, I really emphasize significant figures in units. And that's because I want to build that habit into you from the beginning. What this means is on an exam, 10% of the grade comes from writing units. 10% of the grade comes from maintaining the correct significant figures throughout the problem. And that means if you're going to keep, for round off error, the bar, I'm going to finish this, check the end in the recording. And I'll reiterate it on Wednesday. But you keep significant figures correctly, you keep your units correct, you're guaranteed 10% of the question. If you drop your units and significant figures, you lose 20% of the question. So if the question's worth 1 point, you get 0.8 points. If you don't know how to work the problem, if you just write the units, you get 20% of the points involved just for writing the units. Because that shows me you at least, even though you didn't know how to work the problem, you at least knew what the units were for that problem and could write them. So we will talk about that and reiterate that again on Wednesday. Are there any questions? Any additional questions before I stop streaming? By the way, Zachary, if you're still here, before Wednesday, work out for, that's not force, that's work, distance per time. No, work is force through distance. Distance per time is velocity. But work out what the units would be for distance per time. It's a derived unit. So, I shall see you guys on Wednesday when we will actually do our first homework. I will be posting the quizzes. That just took a little bit more time for me to figure out Brightspace. And then I'll give a reasonable time for you to do them. I'm not going to spring a quiz on you with and you have 2 hours to do it. So you'll have time. Okay? See you on Wednesday, guys.